everyone. My name is Andreas Mantziris. I am from Imperial College London, where I'm finishing my PhD with Arthur. And in collaboration with Tommy Markkanen, we've been working on the cosmological implications of electroweak vacuum instability. More specifically, we've been focusing on deriving constraints on the Higgs curvature coupling Xi by using the Higgs vacuum metastability during inflation. And today I'm going to give an overview of our first paper and give you some preliminary results from our second paper, which is coming up very soon. So the electroweak vacuum metastability is a phenomenon within the standard model of particle physics, where when looking at particularly the masses of the Higgs boson and the top quark, there are a couple of such indications. So first of all, the standard model as a fundamental theory of nature can indeed remain valid up to very high energy scales, where you have to start considering quantum gravity effects. And this comes from the fact that the Higgs coupling lambda runs smoothly with the energy scale mu. You don't have any discontinuities or any asymptotic weird behavior here, you just have a smooth function. So in principle, from any internal point of view for the standard model, it can provide you a consistent minimal model to describe the early universe. So this is kind of motivation for us to use it in these cosmological studies. Considering these experimental measurements of these parameters, for the central values of the parameters within the uncertainty, of course, bounds, lambda turns negative at some point as it runs. And that means that now when you have a negative lambda in your Higgs potential, so lambda is a self-interaction where you have a quartic term for the Higgs. So that means then when lambda turns negative, that your Higgs potential, so here on the right, so the Higgs potential, so you have this Mexican hypothetical here at the origin, which you cannot see now, and have your symmetry breaking where your Higgs resides in, you have the Higgs mechanism, you generate mass for all the fundamental particles. This is kind of the standard story. But now with the lambda turning negative at higher scales, it means that at the higher field values, your potential will turn and go negative and develop this potential barrier. And because it goes negative, since the lambda doesn't turn positive until maybe very high scales, that means that you will develop inevitably a second minimum, which is going to be lower than the electroweak vacuum state. And because we're dealing with quantum fields, since we're talking about the Higgs, that means that when you have a potential barrier between two minima, instead of just the classical way that you go over the barrier, you always have to consider quantum tunneling. And it's always going to be a non-zero finite probability for it to tunnel. So that is what makes the electroweak vacuum state to be a metastable one. When you're talking about these curved spacetime scenarios in cosmology, you always generate this, you always have to consider this term for normalizability issues, where you have the non-minimal coupling psi, which is what we're trying to constrain, which you cannot constrain with accelerator experiments, since spacetime curvature is very small today. And this couples the Higgs field H with the spacetime curvature R, which is the Ricci scalar. A little bit more on that later. So this is kind of basically the motivation. So now what happens when you have this vacuum decay from the metastable to the true vacuum state? So you have essentially a local process at a particular point of spacetime where it decays and then it excites the surrounding spacetime around it. And from your false vacuum perspective, from the outside as an observer, what you see is that the spherically symmetric bubble of true vacuum expanding. Its expansion velocity reaches quickly that of the speed of light, close to the speed of light. And effectively, that means that you have these bubbles of true vacuum expanding at such a speed that you wouldn't see it coming. And because within them you have a lot of exotic physics going on, practical purposes within the standard model, we consider them to be a singularity. You have these very rapidly growing singularities, which are very catastrophic for your false vacuum universe. So how you quantify this? You do it through the expectation value of the bubbles of true vacuum that are just given by the product of the decay rate, nucleation rate for the process per spacetime volume times the spacetime volume. And you're integrating over your past light cone. And the reason is that again, serving as a motivation that we're still measuring the standard model parameters. We are still here. We haven't been crushed by these growing bubbles of true vacuum. Our universe is still in the metastable vacuum state. So that means that no bubbles could have formed in the entirety of our past light curve, because even if one did, then because they grow so far, they would have already reached us and we wouldn't be here. We wouldn't measure the vacuum to be in the electroweak metastable state. So that means effectively that the probability to have 0 nucleation events has to be significant enough for the one. And then that means that you can apply a Poisson probability distribution because you're talking about rare events. And this is how you make contact with the expectation value of the bubbles. And from this constraint, what you effectively get is this constraint that their expectation value should adhere to. So if you do the calculation in the present day, you know, flat case, you have a very low decay rate that it takes longer than the age of the universe for the process to happen. So we're not under immediate threat of it. But because in the early universe you could have significantly higher age due to very different mechanisms, you are kind of forced to consider the cosmological context of this vacuum metastability topic. And this exactly what is the point of this study. We're studying it during inflation to provide some lower bounds on this. Of course, you have to consider the entirety of your cosmological history. We're just focusing on the period of inflation in the very early universe. And in that period, you can write your bubble integral like this, where now you're expressing your space-time volume has to do, it's written in terms of n, which are the if foldings of inflation, a variable to quantify foldings of inflation, going from the end of inflation, set at 0, all the way to the whatever variable start of inflation you have, since you don't know. Observations require it to be roughly 60 if foldings. Then you have the scale factor coming in, you have the conformal time coming in, your Hubble rate, and by imposing this constraint here, you can constrain the remaining free parameter within here, which will be the non-minimal coupling psi that comes through gamma. This has been part of literature and research since the late 70s from the seminal work of Coleman, Kaelan, and De Lucia. And you find that you have these classical solutions to these tunneling processes from false to true vacuum that are called instantons. And specifically in our case, in this curved space-time scenario, on the high Hubble scales, the Coleman-De Lucia instanton, which is a much more complicated expression, approaches the much simpler Hawking-Moss instanton, which is characterized by an action difference given by this. And this also assumes the de Sitter approximation for your expanding spacetime during inflation, because the full curved spacetime calculation is too complicated. So there is this de Sitter approximation happening here. The bounce action is given in terms of the Ricci scalar and the delta V, which is the height of the potential barrier. So in that first plot that I showed you, the Hawking-Moss action, Hawking-Moss instanton, corresponds to a process taking you over the barrier in a classical manner rather than through. It's not a quantum tunneling process, and that's why the height of the barrier comes into place and not something else. So you're calculating by calculating the Higgs potential at the top of the potential barrier minus the value that it has at the false vacuum at the electroweak state. Then you can write your decay rate, your Hawking-Moss, and the Hawking-Moss instanton, which looks like this. So if you go beyond tree level and include one loop curvature corrections and there are other terms, you have here Minkowski terms to 3 loops, which corresponds to the beta functions, the running of the couplings. You have your non-minimal term, your self interaction term, loop corrections, and some other loop terms. So your loop correction is this messy expression. You're going over the 31 degrees of freedom on the standard model. It's a complicated expression. We don't have to worry about it too much. And then we're going to simplify the potential with a couple of ways to be able to make the calculations more tractable. So one thing is that because the scales, the Hubble scales that we are looking at are much larger than the mass scales of the Higgs, we can safely disregard this term, set m equals to 0. And that means that you can set all the other dimensionful couplings to 0 and have this RG flow fixed point where you can safely neglect those. So we're neglecting the first 3 terms, and then so we don't have to worry about them. And then we can get rid of the scale dependence of the potential. through the process of normalization group improvement, where we choose the scale in such a way that the loop correction will vanish explicitly. And you get the RG improved effective Higgs potential, which is just this 3 times quartic, the non-minimal, and there is a correction to the R² term that you cannot neglect. It's relatively generated, but it's a small one, so we don't have to worry about it too much. Here's the overview of the computation. In this kind of summarize also what the work that we've done in the first paper. So first step, you have to calculate, you have to have a effective Higgs potential to calculate the barrier height, because then you plug it into your Hawking-Moss decay rate, and this is kind of the particle physics aspect of the problem. Then you calculate the cosmological quantities of interest according to the inflationary model that you have. We'll be talking about Starobinsky inflation in a moment, but in our first study, we also considered quadratic and quartic inflation. And you complete the calculation of the expectation value of the bubbles through the integral I showed you before. So in green, you have the cosmological dependable parameters, variables, and in red, you have, of course, the decay. So this is where the particle physics comes into place. You impose the constraint, and that means that the remaining free parameter in here, which is psi, that comes to gamma, you can bound that. You obtain this lower bounds on psi. Of course, if you look closer at the results and you do some qualitative tests, you can get some other implications, cosmological implications with respect to when the time of predominant bubble production has taken place, and whether it depends on the duration of inflation and this other feature, which we can talk about later on. As you can see, the cosmology and the particle physics aspects are somehow separated. And this is a relatively good approximation as a first point, but then in our second paper, what we're trying to do is to look closer at Starobinsky inflation. And when you look closer, you don't have exactly this separation between those. So when you're looking at the Starobinsky inflation, you're writing down your action in the Jordan frame, as you do. You have your standard Higgs terms, you have your Einstein-Hilbert term that gives you general relativity, and your coupling, non-minimal coupling, and then you add this R² term, which essentially through the usual techniques in this type of work, conformal transformation, then you get in the Einstein frame the Einsteinian gravity plus some additions in the matter sector. So we follow this procedure with some non-trivial field definitions here. We get the final R theory of your now redefined Higgs, which we call rho, and an inflaton field, which plays the role of the field that drives inflation. And now for your potential, you have recovered the potential of Starobinsky inflation, which of course is what you want to do. But then for the terms in the effective Higgs potential, you have, besides the standard psi r and lambda for the quadratic and quartic respectively, now you have these additions that are coupling to the inflaton behavior. And this will be very significant. It will affect your results. So now you see that you cannot disentangle as much in the first step between the cosmology and particle physics aspects. But the other overview is the same, and so you follow this, and that's how you obtain this lower bounds on psi. And this is what I saw here. So on the y-axis, you have the electroweak value of the non-minimal coupling because it's a running parameter. And on the x-axis, you have the top quark mass. And the reason why we are plotting in this way is because the top quark mass has the largest uncertainty. So at the center, you have the central values, 1 and 2 sigma deviation with the shaded orange areas. And in blue, now we show you the result from the first paper. So it says field theory, it corresponds to Starobinsky-like power law inflation without considering R² in a rigorous manner. And you, the central value had something like 0.06 as a lower bound. So the area below this was excluded, the one above it was allowed. Now, if you go to this full R² derivation, now your bound will jump up here. And now you see there's a different shade of purple here. And this has to do with the way that you are defining the end of inflation to be. So if you are setting it to where the acceleration stops, then you have this bound here, which is the same as for the blue curve. But because you have these additional terms in your effective potential now that are driving the bubble nucleation processes to be predominant during the very end of inflation, your approximations start to break down, and you may not be able to trust these results. So if you are a bit more conservative about where inflation finishes, and you're more within the desired approximation, then you can get something that trusts more, which is around 0.1. This is what this other line signifies. You have some cuts in your parameter space, so this is the conformal point, psi equals 1/6, which signifies the range of the Hawking-Moss validity, so you cannot go above that. And this vertical line here signifies the lightest that the top quark can be, before which the lambda, the running parameter, doesn't turn negative as it runs. That means that you never develop the second minimum, you always are positive, you don't have metastability, you have absolute stability, so then you cannot derive any bounds. And these black areas of the curves just pinpoint a point where the calculation is becoming a bit more complicated and a little bit less trustworthy, because all of the potential along with the potential barrier is negative. So there you have to be a bit more careful about how you're calculating the local maximum and minimum. So you're effectively not being, these are not as trustworthy as the rest of the points, but you see that they follow the trend that you would expect, because psi turns negative as it runs. So coming up to the conclusions, have managed to consistently include one loop curvature corrections beyond the jitter in this r plus r squared gravity scenario, the Starobinsky inflation, for your effective Higgs potential. And in this manner, then if you play this game of vacuum metastability, you can obtain these psi bounds that are stricter in this case because of this extra negative terms that have been generated in the effective Higgs potential. So it was 0.06 before, and now we're around 0.1. Another important point is regarding the bubble nucleation and when it is predominantly happening. And as we saw, it takes place toward the very last moments of inflation, and that means that you have to be extra careful about your de Sitter approximations, because they're starting to break down and you cannot really trust your results, and have to start considering the dynamics of reheating in this calculation if you want to go further. There's also this minor point regarding the conformal point. You're starting to approach it, so at some point your Hawking-Moss approximation also will start to break down. And also there's the same hints that we got in the first paper, with possible hints against internal inflation, since the vacuum decay gets enhanced at very, very early times, which we haven't talked about in this presentation. But I would be happy to take questions. So thank you very much for your attention, and I hope it was clear.